So let's take a look at example F and see if it fits. Now, help remind me, what does this FITS acronym stand for? What do we got going? What's the F part? Fixed number of trials. So for example F, let's take a look at it. It says, assume that different groups of couples use a particular method of gender selection and each couple gives birth to one baby. That method was called the X sort. The method is designed to increase the likelihood that each baby will be a girl. Assume that the method has no effect, so the probability of a girl is 0.5. Assume that the group consists of 46 couples. All right, so there's going to be a few things that we're going to be asked to calculate, and we're going to review some of our calculations as well. But first things first, let's decide if this is a binomial or random variable. Do you have a fixed number of trials? Is there a fixed number of trials here? How many?
46.
46, thank you. So 46 trials, so yeah, that's a fixed number. It's not changing. So 46, so we can give a little check mark to fixed number of trials. Are they independent? Is the gender of one baby going to influence the gender of another baby from another couple? No. So we got independent checks. What's the T for? What's that T? Two possible outcomes. So there's two possible outcomes there, a boy or a girl. And that probability of success, we're going to assume that it stays fixed at 0.5 throughout the trial. So you have the same probability of success all the way through. So looking good there. Looking good. Let's take a look at some probabilities. Now, just to remind you, you can calculate those probabilities this way. It's going to be binom dist, and then x, then n, then p, then false, where p is your probability of success, n is the number of trials, and x is the number that you want to see succeed. So we'll take a look at that. Now for us in our particular case, I'm going to do binom dist of A2, which is going to refer to the previous column, 46, comma, 0.5, comma, false. So that's going to be the generic command that I've typed in for myself. Let's open up section 5.2 link. And let's see, down over here. So here I go. Here's example F. This is the number of successes, that is the number of girls that we're getting. So I call that my variable x in this case. And let's see, I think I want a little bit more. Oh, let's see. All right, it's not cooperating with me, that's fine. So here's your x, here's the probability. To get those probabilities, I'm going to refer back to this. That's my number of successes. The total number in the sample or the trial is 46, probability of success is 0.5, etc. There's your generic command. Does it look like there's a good chance of getting 0 girls out of 46 if we did this experiment? No, that's not a trick question. It looks pretty close to 0. Now, as you move on down, you see higher and higher probabilities. Do you remember how to calculate the expected value, which is the first question we got to answer here? Find the mean and standard deviation of the number of girls in 46 births. How do you find the mean and standard deviation?
The x times the probability of x, and then the sum of all 46.
Yeah. So we got to take this column, we've got to create it. It's going to be your x times p of x, which I have here. And then we're going to sum that up all the way down. And bam, we get 23. Now think about it a little bit. We had a 50% chance of success for our 46 trials. We end up with an average or a mean of 23. Does it feel like there could be a shortcut here in calculating this somehow? Matt?
Divide by 2.
Divide by 2. Or divided by 2 is the same thing as multiplying by 1/2, yeah. So the shortcut for us for binomial random variables only is this. So let's put a little asterisk for binomial random variables only. I get people who want to use this for everything. I'm sorry, it only works for binomial random variables. Mu is going to equal n times p. Wow. That's a lot easier than the x times p of x and then to sum it all up. Yeah. No, thank you. There's also a shortcut for the variance. So for the variance, we can do sigma squared is going to be n times p times 1 minus p. So that's really just the mean times the probability of failure. That's going to give you your variance. Now sometimes, depending on me or the book or the author, you might write that as m times p times q, where q really equals 1 minus p. That's fine. Now that's your variance. This is your mean. How am I going to find the standard deviation?
Square root of variance.
Nice. Standard deviation is going to be the square root of variance. So it's going to be sigma equals the square root of n times p times 1 minus p, or the square root of n times p times q. Nice. Nice. So that's a lot more efficient than what we had to do back before this section, and that is calculate, p of x times x minus mu squared, sum that up, take the square root, etc. That calculation is actually done for you. If you take a look at 5.2, here's that column, x times p of x minus mu. Again, this is your column for x's. So if we highlight this, you can see all the cells involved. P of x times x minus mu. One thing that I want to stress when you do these things, type in the value for mu. Don't click on a cell and reference it to someplace else. Actually type in that value for mu. If you add that all up, you get 11.5, which is exactly what you would have gotten if you took the mean times q, mean times 0.5. Square root of that gives you this. Great. So that's the mean and standard deviation here. Now, let's delete these if you've already got them in there for yourself. Let's go through those calculations ourselves. But we've got our mean and our standard deviation right here. Let's take a look at the second part of this question. It says, use the range rule of thumb to find the values that separating results that are significantly low and significantly high. So let's understand significantly low and significantly high. So significantly low and significantly high. Now the outcomes that we can get here are anywhere between 0 and 46. This is the number of girls you get from couples using the XSort method. 0, 46. We want to know, well, what separates these values? Does anyone know how to calculate the points that separate these values? The significantly low and the significantly high. Yeah.
Is it mean minus 2 times standard deviation?
Nice. Mean minus 2 sigma, and likewise mean plus 2 sigma. So let's find those values. Thank you. So all your commands start out with equals. Let's click this. That's our mean minus 2 times sigma, which is here. Now I'm not dragging this anywhere, which is why I allowed myself to do it this way. So we get 16.217. I'll do the same thing over here, equals the mean plus 2 times sigma. Again, I'm not clicking and dragging everywhere, so it's okay to do it this way. And I get a couple values. I get 16.2 and 29.8. So those are the values that separate my significantly high and significantly low from everything else. But here's a question for you. If you have 46 babies, can you have 16.2 of them or 29.8 of them that are girls? No. So where should I put that cutoff then? Should I put it at 16 or should I put it at 17? Should I put it here at 29 or should I put it here at 30? Where's the significantly high start? Where's the significantly low start? We'll start with significantly low. Where's that going to start? 16. So that's your significantly low right there. Likewise, significantly high, where's that going to start? Yeah, it's going to start at 30. So those are the values that are significantly high and significantly low. You have to go up to the next integer that separates. Cool. Does it feel like the method's working? If you got, let's see. The last part of this question is you have n equal 33 girls. This is part C. Is 33 girls significantly high? Is significantly high. So the method appears to be working. Another way you can kind of see that is you look at the probability of getting, say, 33 or higher from your probability distribution. So let's take a look here at 33. 33. Get in right there. Certainly it's in the significantly high region. But let's take a look at those associated probabilities. So down here, is there a big chance you're going to get 33 girls if it's the 50-50 distribution that we normally expect? No. So for reasons I'm about to go into more later, we're going to look at the probability of 33 or higher, but even if you start adding up all these probabilities, it's not going to be that big of a number. It's a pretty small chance you're going to get that many if this method has no effect. It appears to have an effect, but yeah, these probabilities look pretty small. All right. How are we looking with example F? Got a thumbs up, Garrett? How are we doing back there? Doing okay? Angie? All right, good deal. So one of the things you're going to have to remember for the final, or not for the final exam, we got an exam coming up a week from today, is significantly high and significantly low. More importantly, these formulas right here, this one of these two, and one of these two. But those are things you're going to need to remember for the exam a week from today. Okay, last but not least, please only do this kind of calculation if it's a binomial random variable. If it's not a binomial random variable, then you have to calculate the mean and standard deviation the old way. sum of x times p of x, add that all up, and then this other column, p of x times x minus mu squared, again, add that all up. Finally, take the square root to get from the variance to the standard deviation. Okay. Anything else on example F? Let's move on down to example G. I guess I'll do G up here. 2. Based on a poll, 40% of adults believe in reincarnation. Assume that 4 adults are randomly selected and find the indicated probability. So there's 3 different things that you're going to be asked to do here. Find the probability that exactly 3 adults believe in incarnation, probability that all of the selected adults believe in reincarnation, and what's the probability that at least 3 of them believe in reincarnation. Okay. Well, let's decide if this is a binomial random variable first. So what do we have to do to check that? See if it fits. Nice. So let's see if it fits in problem G. Example G. Is there a fixed number of trials in this case?
Yes.
How many? 4. All right, good. So n equal 4. Are they independent? Well, if somebody asks you how you feel about reincarnation, and somebody asks somebody else at random, is their opinion going to affect you, or your opinion going to affect them? No. You're strangers, not going to know each other, so they're independent. Are there 2 possible outcomes? You either believe in it or you don't, right? So there are 2 outcomes, 2 possibilities, and it's the same probability from one person to the next. Now that's technically not true because you're probably sampling without replacement, but 4 is such a small sample size that this obeys the 5% rule. Same probability of success through the trial. By the way, what's that probability of success? Did anyone catch that?
0.4.
Yeah, 0.4. So P of success equals 0.4. Okay, let's find the probability that exactly 3 people think that that you're going to be reincarnated. Equals binomial distribution. Remember, it's going to be X, N, P, and then false. Let's figure out what we're going to put in for this first one. Oops, not that one, this one. We want to calculate the probability that exactly 3 adults selected believe in reincarnation. So what's that going to be? What should I fill this in as? Marvin's got it. Someone else got it for us too. Go ahead, Marvin. What do I want to fill in there?
Equals binomial is 3, 4.4 false.
3 is your X, 4 is your N, 0.4 is P, and then false. Cool. Bless you. Let's see what that looks like for this one. G. That's going to be right there. Let's erase these two here, just for giggles. Actually, you can erase the third one if you'd like as well. But that first command should give you about 0.1536. I was having problems earlier in my morning class that you weren't getting enough decimals to show up. Is it showing up okay this time? You getting all the decimals that I got there? Safe? Okay, thank you. Let's take a look at the next part here. What's the probability that all the selected adults believe in reincarnation? How's that going to change things? What different do I have to put in now that I didn't, or that I compared to the first one? Yeah, 4 instead of 3, right? This time you're looking for 4 out of 4 successes. So 4 instead of 3. So for part B, it's going to equal binomial distribution 4, 4, 0.4, false. Too many 4s in that one for my taste, but it is what it is. Probably the easiest thing to do here would be to take this one, copy it down here, and then go back and change that 3 to a 4. Oops, I changed it in the wrong one. Let's copy this one back here. There we go. So about 0.02560. Getting that one? Yes. All right, Laney, were you able to get that one? The point. Okay, thank you. Sure? Okay. All right. Let's move on to part C here. So let's see, the probability was 0.0256. About 0.0256. Part C changes things up a little bit. It asks you for the probability that at least 3 of the selected adults believe in reincarnation. So what does at least 3 to mean to you? What does that correspond to in terms of a phrase? Yeah, probability of at least 3 is probably that x equals 3 or x equals 4. Now the thing about x equals 3 and x equals 4 is that they both can't happen at the same time. They're mutually exclusive. If they're mutually exclusive, then I could find this probability by just adding up the probability of x equals 3 plus the probability of x equals 4. Because these are mutually exclusive events. If one happens, the other one can't. Now there's a couple ways you can do this. Actually, there's a good variety of ways you can do this. But let's see if we can't come up with the most clever way. What's the most clever way we can do this right here? Can anyone suggest something? Matt?
Just add the sums together.
Yeah, we've already got each probability. There's probability that x equals 3. Here's probability that x equals 4. If I want the probability of both of them, I'll just sum them up. So equals sum of these two. And that should do it for us. For that one, for part C. So about 0.1536 plus 0.0256, 17920. So nothing wrong with doing that. You could actually type out both of these probabilities if you wanted to. So I could, if I wanted to, I was really motivated, I could say, all right, well, that's equal to this plus the probability that I had a 4 here. It would work that way as well. It just feels easier just to add up those previous two answers rather than type out that command. But if you wanted to, you could type out the whole command. Doesn't matter. I should get exactly the same thing, except my number of decimals is not set the right way. There you go. Now it works. All right, but that's not the answer for part D. Part D is one more thing. So let's move on to the last part here for part D. If 4 adults are randomly selected, is 3 a significantly high number of people who believe in reincarnation? What has to be true if an event is significant? What has to be true about its probability of occurring? What was that low threshold we gave it?
0.05.
Yeah, 0.05. So is our probability less than 0.05?
No.
No, not the cumulative probability here. No. So no. The probability of at least 3 is greater than 0.05. So no, it's not. Nice. All right. Do we have some more data up here? Let's see. Odds, I assume that's a 2. No, it's just oh, odds. Is that a 2? Thank you. All right, so let's see here. We got 5, 9, 10, 20, 9, 7, 16, let's see, 10, 13, and 6. Someone want to read these to me when I get to the other side here? We're going to take a look at how you guys did in terms of the M&Ms. So there's a few of you that got in early. You got my emails and you got to eat your data. So we're going to take a look at M&Ms. Now, a few things you should know about M&Ms. First of all, there's 2 plants that produce M&Ms in the United States, from my understanding. One of them is in Hackettstown, New Jersey, and the other one is in Cleveland, Tennessee, which I didn't even know there was a Cleveland, Tennessee, so I started doing these problems. But they have different distributions of colors. And the distribution of colors has changed over the years. For a while, they took out red. I think blue was out for a while. So it's changed a lot. But what we're going to do is we're going to enter in the numbers that we observed collectively here today. Now, this is the probabilities according to M&M Mars of getting a particular color. And I assume they've done some marketing on this to see what, mix of colors looks most pleasing. And this seems to be, the de facto standard for right now. So help me out. How many red did we observe? 9. Orange? How many? 20. A lot of orange. 16 yellow. 10.
That one's supposed to be 18.
Green was supposed to be 18?
Yeah. We forgot the last 5.
Oh, all right.
Was it
No,
5?
green.
Oh, I mean blue.
Oh. So green is 10.
Yeah.
All right. Blue is 18?
Yeah.
Okay. And brown is 6. All right, so we had 79 M&Ms altogether. Let's delete these. Yeah, let's start all over with those. So what we're going to do is we're going to treat this 79 as our n, and then do a bunch of kind of binomial experiments from there. So if this is my n, remember to find the mean and standard deviation, we're going to use the formulas that we have here rather than play around with anything else. Mean is n times p. Standard deviation is going to be the square root of n times p times 1 minus p. Those probabilities are the ones that are in that second column where I've got things from M&M Mars. So, okay. So what I did here is I took n times p. So it's going to be this number 79 times 0.131. And that gives me, on average, I should expect 10 red. We were actually pretty close to what we would expect. If you have almost 80 M&Ms, you would expect about 16 of them to be orange. Okay, again, we're pretty close. Now, if you take the mean and add 2 times the standard deviation and subtract 2 times the standard deviation, you get these ranges. So let's see how we did. Did we observe any unusual or statistically significant events? Now that would happen if this lies outside of this range of numbers. So was the number of reds we observed outside the typical range? No. Why don't you take a moment for yourself and look down the rest of them. See if we observed any statistically unusual events with our data. So is 20 outside of this range here for the orange? No. How about, are we outside the range for the yellows? We're close, but we weren't quite outside it, right? What would we have needed to be outside it? 17 would have worked. We're not quite there. And the rest of these are comfortably inside the expected range, so we didn't get to observe any unusual events. My morning class did see a couple of unusual events. We got an unusually high number of orange and an unusually high number of blue. So usually they're pretty good at mixing these things up really reliably. So it was unusual to get 2 statistically significant events. This is more the norm in my experience, but you know, hey, not bad. One of the things I expect you to be able to do is exactly what I did, and that is find these values, decide if you have a significant event or not. Is your observed value in this range? If it is, great. If it's not, okay, it's statistically significant. It's either significantly high or significantly low. How are we looking on our M&Ms example? Could you do that a week from today? Find, if something was significantly high or significantly low. All right, I want to see all faces. Mason, all right, looking good. Evan, all right, thank you. Cool. All right, let's put this one to bed then.